So in this section, we're going to look at the opposite kind of metal semiconductor junction, one that's ohmic and does not form Schottky barrier height. So the energetic situation would be here for an N-type semiconductor. We have the case where the work function in the metal is smaller than the work function in the semiconductor. And that means that there's going to be electron transfer from the metal into the semiconductor upon putting these two materials together. Now, in the other sections for the p-n junction and the Schottky barrier, we talked about forming a depletion width on this side of the junction, the semiconductor. But now we're actually talking about adding extra electrons to an N-type material. So we actually are going to form the opposite sense of band bending when we make that transfer. So typically, if we look at a Schottky barrier or a p-n junction, we have the bands bending up for a depletion width where we have Nd plus ionized donors in an N-type material. So this is opposite to what we're going to form in this case. In this case, because we're transferring the electrons, the semiconductor bands are actually going to bend down towards the interface, even though we're in an N-type material. And what this really means is that there's an accumulation of extra electrons here in this region. And we can see that from the band diagram because the distance between the Fermi level and the conduction band is larger away from the junction than it is close to the junction. And this means that the concentration of electrons in the conduction band has to be greater here. So in this situation, we actually have no problem flowing current either way. There's no rectification because the metal can inject carriers into the conduction band easily, and the conduction band can inject carriers easily into the metal. So there's no barrier formation, and either sense of applied voltage will result in a current that flows easily without having to overcome a barrier. So again, the conditions are that for an N-type material, the work function is larger in the semiconductor than it is in the metal. And for a p-type material, it would be the opposite, that the work function in the metal is larger than that in the semiconductor, resulting in an ohmic contact to p-type material. Okay, so that's really what we want to say about ohmic contacts. They do have a specific resistance which can and should be characterized for specific fabrication steps having to do with the details of this interface and how many electrons. So that's all we're going to talk about in terms of ohmic contacts to semiconductors. Their phenomenology is a little less complicated than that of Schottky barriers. And we can form them, remember, in the N-type case whenever the work function in the semiconductor is larger than that in the metal, and then vice versa for a p-type material when the metal work function is larger than the semiconductor work function.